Great, so the next speaker is Christine Muschik, who will tell us about hardware-efficient computing using qubits.
Yes, thank you. Thanks a lot also to the organizers for putting this amazing conference together. I really enjoy it. I totally enjoyed the last talk also. And I'm also going to talk about qudits. And I'm also going to talk about hardware efficiency. So that is actually currently one of my absolute major favorite topics. And so I'm located at IQC, the Institute of Quantum Computing in Waterloo. And if you want to see all the other things that we're doing, despite or on top of qudits, you can check out quantuminteractions.com. Yeah, so I'm thanking everybody who supports us. And here's some advertisement. Yeah, so as I said, qudits is something that I'm very excited about, and I believe qudits is something which is now really only in the beginning, and this is why we're organizing a qudit workshop in Waterloo. So if you're interested in these developments, then save the date. So it's 9th and 10th, and we will bring together experimentalists and also theorists, and it will cover several different areas where qudits can play a role. So it will, of course, talk about quantum algorithms, perspectives for quantum error correction with qudits, but also quantum sensing and quantum networks as well. And maybe this is even only the first event in a whole series. And oh yeah, if Canada is a little bit far from where you are, we also want to make it accessible online, so you can follow it also online. All right, so here is our personal part of the story from our team's perspective. And I'm going to talk predominantly about this publication. So you find it on the archive already. And if you scan this code, it should bring you straight to the preprint. And this is a quick overview to the next, I think, 35 minutes that we're going to spend together. I will start with an introduction and motivation, and then I will talk about how we are using qudits in this specific case for an application, which is the quantum simulation of problems from particle physics, specifically. And I will go in more detail here to simulate gauge fields and matter using qudits. Also, then I want to talk about the D in qudit. Yeah, so like how many levels we can use realistically and how we can study this. And of course, there will be some conclusions. So let's get started with the introduction. And yeah, with classical computing, I mean, nowadays almost everything is binary, right? Zeros and ones. And if we look at quantum computing, specifically at the major players, or really at the main predominant platforms, there's also really this tendency to laser focus on zeros and ones, right? So it's like the same as in the classical case, just putting it in superpositions. And what this entire talk will be actually about is to go beyond the binary. Yeah? And that is really motivated, in my case, by two things. So the first one is the benefits that we can reap from that, but also because it's very timely, because today's quantum hardware is absolutely capable of this qudit encoding. I mean, of course, you can limit yourself to 2 levels and treat it as zeros and ones, but like all these architectures, they really allow you naturally, like really organically, to make use of more levels. Yeah, like qudits, qquins, and so on and so forth. And that is absolutely true for trapped ions, superconducting architectures very naturally, actually. Rydberg atoms, absolutely. Ultracold atoms, nuclear spins, photonic systems, like you name it. So this is what today I'm going to talk very much on ions, because that's so close to our hearts, because this is how we realized our qudits in collaboration with our experimental friends. But everything that I'm going to say really pertains to like a whole host, like a plethora of present-day quantum hardware. Okay, and before I go in any detail, I want to provide you with this take-home message right from the get-go. And that is why I personally became a convert, in a sense, with my old self, like really thinking of qubits, and now I'm very enthusiastic about going beyond binary and using qudits. And why is that? Like, I am and have been and will be interested in, among other things, models from high energy physics and particle physics. So like, I will have problems, like my daily life looks a lot like having problems in lattice gauge series, yeah? And these problems can be treated in ridiculously short depth circuits, yeah? So that was something that was like really an insight that the qudits really could bring models that we consider too complex, like really within reach of what we can do today. Yeah, and I will tell you about this in a moment, so details on all of that. But what was really helpful from our perspective is that, so my old self, basically, she was breaking down everything in qubits, and we got very complex algorithms, and gate depth was always limiting us. So it was not even register size, which was limiting us, but gate depth was like really a major cause of headache. Yeah, and then with the qudits, we just had dramatically more shallow circuits. So we accumulated dramatically less error. And so we could really start seeing results on more complex issues, more complex models. So that's in a nutshell, basically, where I see one of the key advantages here. And so here, I want to point you to a review article, because naturally we'll all walk out being very interested in qudits, no? So if you want to read this one qudit review article, which I can recommend, and Barry Sanders is one of the authors. He visited Perimeter, like Waterloo, a short while ago. If you follow me on LinkedIn, you probably know why I look like this on the picture. But that's not the story of today. The story of today is to talk about what can be done in real life. And if I say in real life, we crucially really depend on the experimental heroes who bring these ideas to life, because in case I didn't mention that, like I'm leading a theory group, like we're a bunch of theorists dreaming. And then in Innsbruck, at the University of Innsbruck, in the team by Martin Ringbauer, who is embedded in the group of Rainer Blatt, and who has an amazing PhD student, Mike Mead. They really implemented all of these things and really made the proof of concept demonstrations that give everything this flavor of reality that that I value so much. Okay, so in short, this is a collaboration which is across the Atlantic between Waterloo and Innsbruck. So we are 6,000 kilometers apart, but it worked pretty well. And yeah, so these are all the people who contributed here. So setting the stage. So I'm not talking about general problems. I'm talking about very particular problems about gauge theories. And within gauge theories, I also don't talk about any gauge theory, no? So for instance, even though condensed matter gauge theories are extremely interesting, for now, like for this talk, I'm going to talk about gauge theories for particle physics specifically. So really the theories that underlie the standard model of particle physics, quantum electrodynamics, quantum chromodynamics. And I also want to spend 1 minute why do we want to have better simulations of those theories? And the motivation, personal motivation again, is actually twofold. The first one is that even though we perfectly well know the laws of the underlying theories, like we know the standard model of particle physics, there are still incredibly complex simulations required to even understand the physics of the universe that we see today. Yeah, so that is really something that there is really an urgent need even today to have better simulation methods, even to understand our universe despite knowing the basic rules. And the other one, number 2, is a little bit more, even more adventurous. That's because we need to understand where the standard model of particle physics fails, right? So, and for this, we need to make very accurate prediction to come to a point where the prediction doesn't match the observation. And this is really like the crack where the light can come through and where we can learn new physics in the end. Of course, I was telling you now the big dream, like the ultimate motivation. And of course, some disclaimers and expectation management is now in order. But this is at least like the dream that is basically guiding, pursuing the quest of better simulations for gauge theories for particle physics specifically. And so the first disclaimer, before I even talk about feasibility, the first disclaimer is I'm not talking about all problems here, right? Because there's this insanely successful field, right, of particle physics, and there are many problem areas there have perfectly under control, and we have no business there, no? So this is really, I'm going to talk about problems which are inaccessible to the traditional lattice gauge theory. So areas that are afflicted by sign problems, so problems with topological terms, real-time evolution, or chemical potential. So for instance, everything which has a time evolution, like as a quantum physicist, I would say time evolution, they call it real-time evolution, like everything dynamical, we introduce sign problems, so basically the standard method go out of the window. This is where I would use a quantum computer, right? I wouldn't use a quantum computer on all problems, but specifically on those type of problems, or high matter density inside the neutron star in the beginning of the universe, again, where I have a finite chemical fermionic chemical potential, again, where there's a sign problem, the standard methods don't do a good job. And this is where we investigate the use of quantum computers. These are, of course, vast problem areas, and like there are many exciting problems in modern physics which really fall into these categories. Okay, and then, of course, as you will see throughout this talk, even within those specific problem classes, we as a field are basically, still babies, no? So like our quantum computers still need to learn to walk before we can even start being useful here. Good. So now I'm motivated using qudits for problems in particle physics. And so let's do that. Let's do that. And this is a fairly young field, even within quantum simulations, it's a fairly young field. And if you just say, yes, I go about it, I want to simulate the lattice gauge theory, then you will see that our community struggles with certain things. So in particular, two of the major hurdles that we are currently struggling with is we need to represent the gauge fields. I mean, it's a gauge theory, no? You better represent your gauge fields. And the other one is quantum simulations beyond 1D. I will explain more what this means in a moment. Yes, because as I said, like the big dream is to simulate nature, and nature, of course, is three-dimensional, but we have to work our way up and understand one dimension first, and we understand 2 dimension, and then we want to go to 3 dimension in order to simulate and understand nature. Okay, so since it's easier on our brains, I'm introducing a one-dimensional gauge theory here. So I put it on a lattice. So it's a lattice gauge theory. And so the vertices of our spatial lattice is shown in black. So this is where all the matter lives. And the links in between is where we put our gauge fields. And for the purpose of being very concrete, let's look at quantum electrodynamics. So like how electrons and positrons interact through electromagnetic fields. And so the gauge bosons in this case are simply the electromagnetic fields, and they live on the links. And here I depicted the eigenstates of the electric field operator for one particular link. And this lives in an infinite dimensional Hilbert space. Yeah. So this is naturally, by the definition of the problem, by the problem that you committed yourself to solve, like a high-dimensional problem. And so again, just explaining what this means, these are just for one link. You have this for each and every link. And it's the eigenstates of the electric field operator that's associated with this link. And it has a spectrum of 0, ±1, ±2, like it's unbounded from below and from above, like it's doubly infinite. Okay, and if you resolve to work in the Hamiltonian formalism, then, well, yeah, you got to truncate. Yeah, so we are got to truncate. And so we immediately see, this is actually something that appears trivial, but I really want to draw your attention to. the minimal truncation that you can really make here in a meaningful way is a qubit, yeah, because either you have no flux, so no electric field, so there's just in the vacuum, or you can have electric field in the positive direction or in the negative direction, and that's basically the minimal truncation. Yeah, so this really is a qubit right there, and if you want to be less brutal, yeah, so maybe you want to distinguish not only between flux or no flux, but you want to give yourself the ability of, okay, a lot of flux, medium amount of flux or no flux, then you're looking at the Q-quint. And like if you want to be more generous, to have more expressivity in your theory, you have a Q-sept and so on and so forth. And of course, like how to truncate is like a whole story. I could give a whole lecture only just on how to truncate, but at the moment, the thing that I want to draw your attention to is that naturally, you clearly have a problem which like is almost begging you to be simulated in terms of qudits, no? Because that's how it comes out mathematically. Okay, and caveat, so I introduced this in 1D, but actually if you're in 1D and open boundary conditions, yeah, you don't even have to simulate your gauge fields. You can, so there's a gauge field transformation that you can make in order to eliminate them. And I would know because, yeah, that is exactly what we did. Like many people do this, like eliminating the gauge fields if you live in 1D simply because you can. It makes your life so much easier. And that was, for instance, what we did in 2016. So this is where my personal journey with this began. So this was a work which was theory and experimental, 2-in-1, basically where we brought the lattice gauge theory for particle physics on a trapped ion quantum simulator. I mean, 2016, it was very small, it was 4 ions, yeah. And we did a quantum simulation of 1D QED and looked at real-time dynamics of electron-positron pair creation. And since 1D and 4 ions really sound so minimal, I want to take this opportunity to brag a little bit because it was still considered one of the top 10 breakthroughs in physics in this year, like teaching a quantum simulator how to do that. And there was also a very nice article in Scientific American, which I will come back to later. Brag. Yeah. Okay, but already, like obviously we were very happy, it was very inspiring, but of course, immediately, like the moment basically the paper was on the archive, we were already saying, okay, like that was 1D, but of course we want to do 2D. I mean, at least, no? In principle, we want to do 3D. But going from 1D to 2D, and 3D is like really like a step function in terms of importance, because in 1D, there is no such thing as a magnetic field, yeah? And obviously, I want to see magnetic field. I need to study like both sides of the coin, no? That's really brutal what you do in 1D to your theory. And of course, Fermi statistics starts to play a role. Like it gets way more interesting beyond 1D. But it so happens it got several technicalities also get much more complicated too. Yeah, you got to really work hard in order to see like this more interesting physics. Okay, and so this is just to say, yeah, there is no magnetic fields because magnetic fields we only see when we have a plaquette and something, flux can go in a circle. And yeah, this is basically what we did next. We looked at the gauge theory on a 2D lattice. So first learning how to do 2D, of course, with the goal to learn how to do 3D. And then it will just look like you expect. You have your matter on the vertices and you have your gauge fields, lots of gauge fields now on the links, and each of them is infinite dimensional. And now, ladies and gentlemen, you cannot eliminate the gauge fields. Yeah, you could in 1D, but in 2D, that it's not going to work for fundamental reasons, but it's a good thing because, so imagine, for instance, you have one plaquette with open boundary conditions. So there must be 1 degree of freedom left to describe the flux, the magnetic fields that pierces your plaquette. Okay, so like if you go beyond 1D, there is no such thing as not simulating the gauge fields. Yeah? And this is just a fun fact from my life, because this was in 2016. And the journalist was asking me about the next steps and said, yeah, Muschik says her team is already making plans to use 2-dimensional configurations, because that's obviously the next thing that we do. And well, well, that was 2016, and like took until 2020, end of 2023 until we were finally done with it. So it took a while. Okay, but it took a while, and Qudits actually came to our rescue. Yeah, so and this is also the moment when I became very enthusiastic about Qudits because they were so helpful here. Oh, and if you want to see like a broader picture of the entire story of like how the field is evolving, so there's, for instance, one review article which I can recommend, and there are others too, because I'm kind of showing you everything through the lens of our journey at the moment. Okay, so as I said, and as you will also see in this review, like going to 2D was like a big thing that you obviously want to do. And there was also impressive advances, like not only by us, but of course by many other people whom I want to properly acknowledge here. And so these are very interesting experimental demonstrations. But the thing that was missing is it's like 2D with only the gauge fields, but the matter was trivial, or going to 2D with the matter, but the gauge field was trivial. And of course, what we need is a full gauge theory with the matter and the gauge fields together, and that is what we set out to do, and which unfortunately took slightly longer than we thought. Okay, and I'm also talking about like these gauge groups, continuous gauge groups, like really for particle physics. I mean, there's also the whole story about doing condensed matter gauge theories, and of course, there in this other area you could do 2D, but it's like a bit different challenge. Okay, so like here's the system which was really incredibly helpful. So it's an experimental qudit system, and this particular one is based on trapped ions. And so what we're looking at here, perhaps a little surprisingly, is a linear ion trap, like the trapped ions, like your qudits are really like a string of pearls, basically. And then sometimes I get the reaction, oh, wait a minute, you're simulating a 2D system, but you're using a 1D system to simulate. And well, the reason why we can do this efficiently is because in trapped ions, we have, of course, all-to-all connectivity. And yeah, connectivity is always very helpful. And therefore, we can have in our simulated model an arbitrary geometry. And the other thing that we, of course, needed was high fidelity entangling gates. Because if you look at the review that I recommended in the beginning, so very early on, there was this notion, oh, wait a minute, if I have qudits, I have small register sizes, lots of things get easier, like you can have improved error thresholds for error correcting codes, can have shorter gate sequences. But of course, it always used to be very challenging to implement those. And as long if you have only crappy gates, if you have only few of them, it doesn't help you. No? So one key component was really to extend the qubit entangling gates that you have in trapped ions to qudit entangling gates, but of a type where you really have high performance. Yeah, so you can really do high performance entangling gates, and in this case, we really found. So, if you wait a moment, you will see I'm going to show results with qtrits and with qquins, and the performance is really very comparable to the qubit entangling gates. Like in my humble personal opinion, that is really why we are in business now, and this is why I think that is now the start where we can start to really do things. Oh, and one more thing, in case you wonder what type of gates, it's not, as you might first think, extension of the Möller-Sørensen gate to qudits. It's actually an extension of the Sirac-Zoller gate, which we lifted to qudits, and which did a really nice job here. Okay, but that's details. Let's go back to the bigger picture. So the bigger picture, like imagine you're the user. Yeah, you want to use the processor like this, you can actually use it in a mixed way. Yeah, so for instance, in our case, we did different experiments with we are the theorists, our experimental friends did different experiments, but the first one has like 4 ions in the trap, and you can use a subset of them as qubits, and you can use another subset as your qudit. Yeah, and you can also, for instance, you could choose to have 2 qubits, 2 qtrits, and 2 qquins. For instance, it's all calcium-40 atoms. It just depends which levels you decide to use, and the addressing is a little bit different. And in our case, we use, so we want to simulate a basic building block of our two-dimensional lattice gauge theory, so which is one plaquette, which has 4 matter sides, and matter is conveniently expressed in qubits, no problemo. And the gauge field, so here you see the minimal truncation, which is a qudit. Okay, so, and this is really how we could address these 2 major hurdles, like representing the gauge fields, because it's very natural in terms of a high-dimensional system, and that allowed us to go simulations beyond 1D, finally, because as you will see, the gate sequences get very short. Okay, so how did we simulate both gauge fields and matter to achieve this milestone? So as I said, it was a 5-year journey, and there were some series steps necessary. I'm not going to go into it. I just wanted to tell you that if you're someone who is interested in the series steps as well, you can go to these 2 papers where we derived like the encoding and how to make it efficient. And there are lots of things to be done very carefully. But from a bird's eye perspective, basically you have your lattice. We divide the lattice into an even sublattice and an odd sublattice, and the theory U1, so quantum electrodynamics, has in the matter side electrons and positrons. We use a staggered fermion formulation. We didn't invent this. It's basically using what the high energy physicists also want to use. And in this case, you can put your particles on the even lattice sides and your antiparticles on the odd lattice side. You map it to qubits through a Jordan-Wigner. And then basically you have your matter taken care of quite efficiently with qubits. Okay, then there's a Hamiltonian, which you want to simulate, and it looks pretty straightforward. It has an electric field part, a magnetic field part. You also have a part which describes the bare mass of your particles and a kinetic term. And well, it just looks like so. I can go into details later if someone is interested. For now, there's only one thing to be pointed out on a high level. So this is a gauge theory, and hence it's a little bit different than simulating, I don't know, condensed matter or quantum chemistry, because we have the gauge constraints, like we have Gauss law. So that is really making these type of simulations very different, because you have your Hamiltonian, and on top of that, so here Gauss law, if you go mentally back in 3D and in the continuum, then it takes this form, that's a divergent of the electric field as a charge density. Yeah, so like the charges are the sources and things of the electric field. And you can basically put it in 2D and make it discrete and make it quantum. And then this exact same thing translates into that all your states that are allowed, that are physical states, that do not violate the Gauss law, have to be eigenstates of certain symmetry operators. And in our case, we are in the charge 0 subsector, so they have to be eigenstates with eigenvalue 0. And like the symmetry operator basically looks exactly like this guy. So this is like a divergence, this is like a charge density. Okay, so having said that, so we want to simulate now a basic building block. The basic building block is one plaquette. So here, in principle, I would have 4 gauge fields, but there's Gauss's law, which I just introduced. So you can eliminate 3 of them. So we have 1 gauge field left, which is represented by a qudit here. And this is a bird's eye view of the experiment. So we're using a variational quantum eigensolver. Yeah, so hybrid quantum classical scheme. And we're using it on, like it's doubly hybrid because it's quantum classical, but it's also hybrid qubit qtrit. So we have a variational circuit. So I can tell you more, like if anybody's interested, I can tell you more about the circuit later. But the short version is that we have a certain Hamiltonian, and the Hamiltonian has certain symmetries. And we just read off from the Hamiltonian what the circuit would look like. Yeah, so it's you don't need anything special. It's really circuit inspired or physics inspired. And then we use this circuit to find the ground state. And once we found the ground state, we determine the plaquette expectation value in the ground state. So why do we do this? For two reasons. So the first one is we were really very eager and keen to access true 2D quantities, because that's exactly what we could not do before, or what nobody could do before. And on the other side, this is also a quantity of interest to the high energy physicists, so to touch base with their community. We also have an error model which fits very well. There's also a whole story how to make a good error model for qudits, because they behave very different than the qubits. And the take-home message here is that even in the simplest instance, oh yeah.
Could you explain how you impose a gauge constraint?
Oh yes. Oh yeah, with pleasure. So there are so many ways how you could do it, and the way how we chose to do it is okay. So we have our system, and in principle there are 4 gauge fields, right? Like each and every link, per definition, has a gauge field. And then I can take the Gauss law. So I have a Gauss law for each and every vertex. And I use this constraint in order to express these operators in terms of the other operators. Yeah, so I'm, or more formally saying, I'm introducing a gauge transformation which transforms all these 3 gauge fields out of the theory. So I get a theory which has only operators for the 4 matter fields and 1 gauge field. So I receive a new Hamiltonian, and the new Hamiltonian does not include these operators because they have been expressed in terms of the other degree of freedom. And the Hamiltonian will look more complicated, but it has fewer degrees of freedom. So I'm eliminating the gauge redundant degrees of freedom. And as a result, the resulting new Hamiltonian is automatically obeying the Gauss law, so to speak. Or there's actually a nicer.
But the key question is, if you have a 2D and impose a constraint for every lattice, and then the Hamiltonian might not be local.
Oh, exactly. It's totally non-local. Yes, and excellent point. Yeah, it's absolutely super non-local, because you can have a long-range correlation, a long-range term, which basically can reach across the whole lattice. So you're sacrificing locality.
And also multi-body terms.
Yes and yes. So let me go to the non-locality first. So in trapped ions, this is not a concern, right? Because in trapped ions, I'm given all-to-all connectivity. So this is one of these examples where the method matches the platform. Yeah.
But if the Hamiltonian that simulate your quantum device is geometrically non-local, what was the original motivations to actually use Q3 to start with? Because it doesn't match anyways.
Can you say this again?
So if the Hamiltonian that you variationally optimized ground state for,
like the encoded one, which is non-local.
That's right. That's totally non-local Hamiltonian.
Yes.
Right. And if that's the case, we are using just variation ansatz to the optimized ground state, right?
Correct.
And as we learned from, for example, QAOA algorithms, there's no particular reason for our wave function locality has to reflect the object that we are optimizing, especially the object lost the notion of locality.
Yes. But so there are 2 separate topics, right? So there's the reason why it's so efficient to use qudits here. And this reason is simply because I'm not breaking a high-dimensional operator into Pauli matrices. Yeah, and so like this argument has nothing to do with VQEs. Like actually, the next thing that we want to do is time evolution. Actually, yeah. So that is for historical reasons that we did a VQE. Actually, yeah. So, but all these arguments 100% carry over to Trotter or whatever you want to do, and also the problem with breaking, like if you take the theory and it has perfectly reasonable terms, like for instance 2 body terms in terms of the large spin operators, but if you're like my old self and break everything down in Pauli operators, you create a huge mess. And one of the things that you do, for instance, if you start from a 2 body high spin, then you of course create 3 body, 4 body in terms of the Paulis, right? So it's like you as a user creating an enormous overhead by insisting simulating a high-dimensional object with spin 1/2. So that's the key message here, is that there are certain theories, and like Susanne had another example, but like if I have a gauge theory, and the gauge theory comes naturally with a high-dimensional object. So like, say we go with the most minimal case, like qtrit, no? Like you have a spin model, and it has qtrits in it. And then, like what my old self always did, she took the qtrits and breaks it down in Pauli's. But for a near-term device, that's not recommended. Yeah, okay, and then there's a whole different story that it's a VQE, and which is separate from that. Yeah. Mm-hmm. Yeah, and like all these things with locality, non-locality, oh yeah, I have 5 minutes left. So there's one more point that I need to make. Non-locality and so on, that's the same for spins and qtrits or qubits or qquint, like you inherit, like this is the same. Okay, long story short, two key messages for my last 5 minutes. The first one is you just reduce the gate count, but that's because you just refrain from doing something very unreasonable. Yeah, because this theory, as I said, is asking you to be simulated in qtrits. And like we're also not simulating the qtrits here, but we are actually using qtrits. Yeah. So, and even in the absolute simplest system, as absolute simplest instance, you go, for instance, from 96 to 26 gates. It becomes more dramatic in other instances. But then there's also the question, naturally, we ask ourselves, can we increase the D? Yeah. And this is a bit switch of gears, because before I was talking about, oh, I want to have a gauge theory which has matter and gauge together. So this is like dealt with. I'm switching gears and I'm talking about, can we study using higher spins? So basically going from here to here. That's what we studied. Yeah. And so it's like interesting experimentally, like are the gates still performing well, but also for a gauge theory, like these gauge theories, they basically need that as a knob, basically, because for some effects, I mean, I chose one where with qtrits you can really see the relevant physics, no? But for some effects you say, oh, I really need a qquint, or maybe I need even 7, and like you can study this now. Okay, so basically in this case we went to a torus. So again, one plaquette, but with periodic binary conditions in all 3 dimensions. I mean, closed loop everywhere. And so I removed the matter fields because now I'm concentrating only on the gauge fields. And yeah, how the system looks like, you still have 4 vertices, you have 8 links, which means 8 gauge fields, like you see it over there. But we have a Gauss law, which allows me to eliminate some. So I have 5 independent gauge fields. And if I look at the ground state, then it's enough to simulate 3 gauge fields. Again, if I want to do time evolution, I should use all 5, no, not only 3. Okay, and then there's a lot of theory happening. There are better operators to be used. We call them rotators. You don't need to care about it now. It's just the message that I want to convey here is, so there's a new circuit. And in this circuit, there were 3 qudits used. So first as qtrits and then as qquints. And then we could basically see how our results get better if we use qquints, yeah, because how well we can capture the ground state really improves if we use qquints, because it's a more accurate description. So we have a whole theory paper just about that, and I was extremely happy to see this in the experiment, because a couple of years ago I would not have believed that we have a full-fledged VQE, which here we take as a representative as a digital quantum simulation, yeah, and it's a full-fledged optimization with qquints, yeah. So I would not have thought that I will see this not even so quickly, and I'm skipping over that, but that's just how one sees that the gauge theory, you get indeed nicer result if you use qquints, like you really get something out from going through the effort of using 5 levels. Yeah, but the take-home messages are, we have a full VQE ground state search for 3-level qubits and 5-level qubits, and it even worked. And these qudits allow you to seamlessly observe the effect of different gauge field truncations by controlling the qudit dimension. It's like really very seamless. No, it's like all one setup. And the conclusions are twofold for the purpose of this talk. So in the first part, I talked about including both dynamic gauge field and matter field. So yeah, we did that. So I'm especially happy that we did that because that's what I promised to IQC when they gave me the position. And the other thing is what I didn't even know that we could do it in the beginning is that we can really adjust the discretization of the gauge fields, and the gates also work beautifully even for d = 5. And I see great potential, and like you could say, okay, after 5 years, we finally finished this project, but I think it's just the beginning. Yeah, I think, okay, now we have seen that we can do these things on paper and in the lab. And yeah, I'm completely motivated to even get started on this. And this is precisely why I want to do this workshop in summer, like also to bring the community together in this. And the long-term vision from my side is, I mean, you know, what I dream about now, simulation of nature in 3 spatial dimensions. So we have, like, going from 1 to 2D is much more difficult than going from 2 to 3. Then, of course, we will have to scale up the system size because now we focused on the basic building block. I mean, having the basic building block is great, but like we need larger lattices, obviously. But if we want to go to larger lattices, being resource efficient is even the more important, actually. And in terms of the qudit techniques, so the key tools can be implemented on many quantum computing platforms. Yeah, it doesn't have to be trapped ions. They're directly applicable to digital quantum simulations of real-time dynamics, if you're into this. And from my perspective, this is quite an exciting perspective because then we get really sign problem afflicted, and this is where we can leave the classical computers in the dust, hopefully. And oh yeah, one reason why I was also so intrigued by Susanne's talk is that, so I talk about particle physics, right? But there are many areas like, for instance, in chemistry or material science, where basically you have these models where these high-dimensional systems just show up, yeah? And we have now a choice not to break them down brutally into qubits, but to treat them, especially on near-time devices, exactly as they are. Okay, so that is all I wanted to say. And I'm thanking especially the University of Waterloo, IQC, program TQT has been heavily supporting us, and the Parameter Institute, where I'm also 1 day per week, and our sponsors. And of course, I thank you for your time.
Thank you for the talk. That was very interesting. Lots of people are doing resource estimates for where you might be able to get into that exciting regime. And I at least haven't seen qudit resource estimates for this sort of problem. Have you looked at that, and do you have a sense of where, you know, might that be a nearer term fault tolerant target, or?
Oh. Yeah, so I don't, like, we made a resource, we are so much in the beginning, like pre-beginning, basically. Like, we made a resource estimate without any error correction on top of it for our specific problem, and especially for the pure gauge theory with periodic boundary condition. Oh my God, that was just very inspiring. So this is why we want to do more in terms of gauge theories for that. But I mean, that was just for our particular problem, no? And it will be very interesting, I agree, to make a more proper resource estimate and then put error correcting code on it. And then, of course, like, how would it look like if you were to do it fault tolerantly? Yeah, I would consider this extremely interesting.
We'd love to talk with you about that. So, yep.
Yeah, let's do that.
Yeah, so in the last part, it seemed to me you could understand that ground state as maybe being a pure Z3 or a Z5 gauge theory. And so I was wondering whether you'd benchmark maybe on Z3 surface codes or Z5 surface codes? Because it seems like you can realize those kinds of things too.
Yeah, we have not even thought about it. Yeah. But maybe that's a good idea to talk. I don't know what's
Thanks for a nice talk. You mentioned that when you take into account those gauge fields, you end up with non-local Hamiltonians.
Yeah, big time.
So do you expect to get like a measurement problem? I'm talking about like sample complexity, analogous to what people observed in quantum chemistry. I mean, like many non-commuting operators that you have to estimate for larger systems. And like, what are the natural measurements that one takes? Like,
Yeah, they're very interesting point. So there are two things to say about it. So yeah, there are a number of measurements that, like for instance, say you want to do a VQE for, like you don't have to, but let's say you want to do one, then the number of measurement groups that are like is getting pretty large. And the other thing is for evaluating interesting observables, we have actually a related project on how, which is related also to what Robert said yesterday. Actually, like if I have a quantum simulator, but now I need to read out my observable with not taking too much time. So like what is the statistics that I need? So that's a complex question. And so we started to look into this, and like I'm really interested in that. But the other thing that I wanted to say, so here we eliminated all the gauge fields that we can and got maximum non-locality. I would not, like I don't have to do that, no? Like that's like there are two extremes, like eliminating none of the gauge theory, I'm totally quasi-local, or eliminating all of them, like I get super non-local, but you can also eliminate just a subset of them and then you're somewhere in the middle. Like choose your adventure. I think this was for you were first, no?
Yeah, so thank you for the talk. I was wondering, since you're using a trapped ion platform, is there any benefit from potentially using the phonon modes as qudits?
The phonon modes as qudits. Yeah, so on the one side, they are nicely infinite dimensional, right? And okay, so there are pros and cons. Actually, we have a paper on simulating the Higgs model where we use a photon mode, like not a phonon, but a photon. And like we explored a little bit how to do that. So we have kind of a sense for that. Yeah, so there, it makes the model, like short answers makes the model a bit more complicated. And in terms of the trapped ions, you need an awful lot of gauge fields if you make your lattice bigger, and then you have to have really precise control of your, because for each new link that you choose to include, you need a new phonon mode, yeah? So that's maybe a second challenge. But it's not very much explored, no?
Okay, thank you.
Do we have time for one more? Like our...
Maybe it's about it for now.
Okay, yeah, I could
So
see
let's take,
you look
let's take the rest
uneasy.
of the conversation offline, and we'll see you back at 2. Thanks.